To see the usefulness of the new theory, with x1 through xn, the solutions to the linear system x dot equals ax, where I'm assuming that the matrix A is n by n, then these functions are linearly independent if and only if the Wronskian is not zero. The theorem is easy to prove. Suppose you have C1 x1 through Cn xn equal to the zero vector. We can write this in a matrix form. The matrix x1, x2 through columns xn times the vector c1, c2 through cn equals the zero vector. By a theorem from linear algebra, this homogeneous linear system has a unique solution, the zero vector, if and only if the determinant of the coefficient matrix is not zero. But the determinant of the coefficient matrix is the Wronskian. So this has only the solution C1 equals C2 equals Cn as solution if and only if the determinant of the coefficient matrix, i.e. the Wronskian, is not zero. This last theorem might leave you a little disconcerted. What if the Wronskian is zero for some t's and not zero for others? We're going to show that for solutions to these homogeneous linear systems, that never happens. But to do that, we need to build up a little machinery. However, just as before, we need an Hobbles Lemma. Now, the trace of an n by n matrix A, which has entries A, I, J, it's denoted by the trace of A and defined by the trace of A is A11 plus A22 plus ANN, i.e. it's the sum of the diagonal elements of the matrix A. So for example, if I have the matrix A equals 4, 2, 5, 1, 4, 5, 5, 1, then the trace of A is going to be 4 plus 1, which is 5. It is a theorem from linear algebra that the trace of a matrix is the sum of the eigenvalues of A, including multiplicities. So for example, if A is the matrix 3, 1, 0, 3, the trace is equal to 6, whereas these eigenvalues, lambda equals 3, has algebraic multiplicity equal to 2. So you get 3 plus 3 equals 6. Just as in the nth order linear case, we need an Hobbles lemma. Let's suppose that x1 through xn are solutions to x dot equals ax then either the Wronskian is identically constant, which means that if the Wronskian is 0 at one location, it will be 0 at all locations, or the Wronskian is a constant times e to the trace of the matrix A times a scalar t. Recall that the trace of a matrix is the sum of its diagonal values, and by a theorem from linear algebra, the trace of a matrix is also equal to the sum of its eigenvalues, including the multiplicities. Now, in all honesty, we cannot prove Hobbles Lemma yet in its full generality, but we will prove a special case and defer the remainder of the proof until later. The proof is for the special case where we suppose all of these x sub k are of the form e to the lambda kt times vk, where lambda and vk are eigenvalue and corresponding eigenvectors. The Wronskian will have the form, the determinant of e to the lambda 1t v1, e to the lambda 2t v2, all the way over to e to the lambda n t vn. When calculating a determinant, if you have a common factor down any row or column, that factor can be brought out of the determinant. Since the first column has the common factor of e to the lambda 1t, that can be factored out. But so can e to the lambda 2t from the second column. So e to the lambda nt and the last column will end up with v1, v2 through vn inside of the determinant still. Well, this is just some constant, whatever it is. The eigenvectors are just some constant vectors. But out front, we get the sum of the exponents. So we end up with lambda 1 plus lambda 2 plus lambda n times t times this determinant. And since the sum of the eigenvalues is equal to the trace of the matrix, the proof is finished, at least in this case. The problem is there do exist in certain instances solutions that do not have this form, as you will soon see. We can now prove the theorem that you've been waiting for. If x1 through xn, if these are linearly independent solutions to the differential equation x dot equals ax, where a is n by n, and if x hat is any other solution, then there exist unique constants C1 through Cn such that x hat is C1 x1 through Cn xn added together. This tells us that if the matrix A is n by n, and if we have n linearly independent solutions to x dot equals ax, then we have them all. Every other solution can be represented as a linear combination of these n that we have. This is exactly what we want to know. The proof is very much like the proof for the nth order linear case that we did earlier. We're going to set x naught to be x hat of t naught for some t naught. Then consider the linear system of equations x1 at t0, x2 at t0, through xn at t0 times the vector c equals x0. This is a linear system of equations for the n unknown, c. According to a theorem from linear algebra, this system will have a unique solution c if and only if the coefficient matrix has an inverse. Equivalently, if and only if the coefficient matrix has determinant not equal to 0. But the coefficient matrix has a determinant called the Wronskian, and the Wronskian's not 0 because these functions are linearly independent. So since the Wronskian is not 0, there exists a unique solution c to this linear system. This vector is c1 through cn. We're going to set x tilde to be c1 x1 through cn xn. So this x tilde is a linear combination of these solutions. And since it's a linear combination of solutions, x tilde is also a solution. Now, x tilde at t0 is x0 because it satisfies the system of equations, and x hat of t0 is x0 by definition. That's how we got x0. Both x hat and x tilde are solutions to the differential equation, and they both satisfy the same initial condition. So by the existence uniqueness theorem, x tilde equals x hat, and hence x hat is c1 x1 through cn xn, and the proof follows. We now know exactly what to do in the distinct eigenvalue case. If x dot is 4251 times x, we already know that lambda equals -1 and 6. We have x1 equals -t times 2 negative 5, and x2 equals e to the 6t times 1, 1. By the last theorem, we can represent all solutions as c1 to the -t times 2 negative 5 plus c2 e to the 6t times 1, 1. Every solution will be in this list. We already showed that eigenvectors coming from distinct eigenspaces are linearly independent. If you have n distinct eigenvalues, then you can generate n distinct and linearly independent eigenvectors, which yields n linearly independent solutions. To form the general solution, all you have to do is take an arbitrary linear combination. This leaves two cases by trichotomy. First, the complex root case, and second, the repeated root case, and we'll take those in order. So, what happens in the complex value case? Here, suppose we have lambda plus or minus equal to alpha plus or minus beta I. First, a bit of notation. If z is a complex number, it can be represented as x plus iy, where x and y are real. The complex conjugate is x minus iy, where you switch the sign of the imaginary part of the complex number. So if I have an eigenvalue lambda, which is alpha plus beta I, then its conjugate is alpha minus beta I. We will assume that beta is positive for sake of clarity. Suppose that AV is lambda V. If we take the complex conjugate on both sides, we'll have the conjugate of A times V conjugate is the conjugate of lambda times V conjugate. But the conjugate of A is itself, we're assuming that our coefficient matrix have real entries, and the conjugate of a real number is itself, since the imaginary part is 0. So what we have here is A times V conjugate is lambda conjugate V conjugate. This tells us something important. If lambda is an eigenvalue corresponding to the eigenvector V, that implies lambda conjugate is the eigenvalue corresponding to the eigenvector V conjugate. So if you have one eigenvalue and its corresponding eigenvector, and if they are complex, you get the other pair for free. They're just complex conjugates of each other. So, another bit of notation. Let's suppose that V has pieces that we can rewrite as U plus I times W. Yes, we'll get a solution, e to the lambda TV, but remember lambda is of the form alpha plus beta I times T, and V is the form U plus I times W. Now, it's important to see from Euler's theorem that we can rewrite this as e to the alpha t, e to the beta t times I, U plus IW, which is e to the alpha t times cosine beta t plus I sine beta t times U plus IW. When multiplying complex numbers like this, it's better to FLIO instead of FOIL. FOIL is the acronym first, outer, inner, last. For complex numbers, in order to combine the real parts first and then the imaginary parts second, it's better to do first, last, inner, outer. And if we do that here, we'll have e to the alpha t, we'll have U cosine beta t. When we multiply the imaginary parts together, we'll have an I times an I, which is -1. W sine beta t. But there's more. There's the imaginary parts. We have to multiply by the inners. The inners will have I times U sine beta. The outers will have I times W cosine beta. We'll factor the I out. And what we'll have left is U sine beta t plus W cosine beta t. Now we've played this game before. You might anticipate how this is going to work out. So far, this gives us one solution. It's good, except it's complex valued. We need a real valued solution, but we can get another solution very easily. We have one solution, x1, this form. To obtain the second solution, we use the conjugate eigenvalue and the conjugate eigenvector. We obtain the conjugate eigenvalue by replacing beta by negative beta. And we replace the conjugate eigenvector by replacing W with negative W. Let's see how that plays out. It doesn't do anything to the e to the alpha t part. The real part of the eigenvalue always leads to some exponential factor. The imaginary part leads to your oscillation. If beta is replaced by negative beta in this first entry, Since cosine is even, the negative goes away, and you just end up with u cosine beta t. In the second term, if beta is replaced by negative beta, you get a negative that comes out, but you also need to replace w by negative w, so you end up with two extra negatives, so it still ends up minus w sine beta t. It all depends upon what happens with the imaginary part. If beta is replaced by negative beta, you get a negative u sine beta t. If beta is replaced by negative beta in the second term, cosine being even, the negative goes away. But w is also replaced by negative w, so you still get a minus w cosine beta t. These last two terms both have a minus. We'll factor that out. And so these two differ only by the sign of the imaginary part. I'll bet you can figure out how we're going to construct real-valued solutions from these two now, especially if I put a big line underneath. You guessed it, we can form y1 by taking the average of x1 and x2. That gives e to the t u cosine beta t minus w sine beta t, and y2 is 1 over 2I times x1 minus x2, which is e to the alpha t times u sine beta t plus w cosine beta t. It might help you to remember this if you know that the rotation matrix that rotates coordinates through some angle theta is given cosine theta minus sine theta, cosine theta. If I set xy equal to cosine theta minus sine theta, cosine theta times x prime y prime, I get the rotation equations from pre-calculus. You might remember these when you were working on the rotations of conics way back in pre-calculus. This is literally how you may transform or rotate coordinates for computer graphics. So for example, if x dot is 4, 1, negative 2, 2 times x, the first thing we need to do is find the eigenvalues. So we'll subtract lambda from the diagonal elements and take the determinant. This gives 4 minus lambda times 2 minus lambda, and then we subtract a negative 2, which gives us plus 2. We'll have a positive lambda squared. Negative 4 lambda minus 2 lambda is negative 6 lambda. We'll have 8 plus 2 is plus 10. Now if I complete the square here, dividing negative 6 by 2 is negative 3. Squaring that is positive 9. I wish I were adding 9, not 10. So I'll split this into plus 9 and plus 1. This gives me lambda minus 3 squared plus 1. If we shift this to the other side, it becomes negative 1 when we move it over. Taking the square root, we'll have lambda minus 3 is plus or minus the square root of negative 1, which is I. This gives us the eigenvalues 3 plus or minus I. Alpha in this case is 3, beta is 1. We still need to find the eigenvectors. With lambda equals 3 plus I, recall that we have to solve a minus lambda I 0 in order to find the eigenvectors. So we have to subtract the eigenvalue from the diagonal elements. Subtracting 3 plus I from 4, we end up with 1 minus I. This stays as 1, and we have 0 here. Keep in mind we don't really need to write the second row, because we know that it will be linearly dependent, so we can reduce it to a row of zeros by an elementary row operation. This gives us the eigenvector 1 negative 1 plus I. You switch these and change the sign on 1 all the way across. We can decompose this into 1 negative 1 plus I times 0, 1. 1 negative 1 and then 0, 1, factoring the I out. This is the vector u, and this is the vector w. It is at this point we can write down the solution to the differential equation. You just need to remember that formula. Remember, we have lambda equals 3 plus I with the eigenvector 1 negative 1 I times 0, 1, where this is u and this is w. It follows that the general solution is going to be C1 e to the 3t times cosine of beta, beta is 1, t, times the vector u, 1 negative 1, minus the sine of beta t times w, which is 0, 1, plus c2 e to the 3t sine of t times 1 negative 1 plus cosine of t times 0, 1. Notice that there's a certain advantage in the complex eigenvalue case. We don't need to find the second eigenvector because it's just the conjugate and it has already been worked into the formula for our solution. We now look at the repeated eigenvalue case. As you'll see, the issue is not so much that the eigenvalues are repeated. The problem arises only when you don't generate enough linearly independent eigenvectors. Let me give you an example. Suppose we deal with x dot equals 3, 0, 0, 3, x. As we've seen before, the eigenvalues are 3 with algebraic multiplicity equal to 2. The eigenvectors are 1, 0, and 0, 1, which means we have geometric multiplicity also equal to 2 linearly independent directions. This gives us a general solution of C1 e to the 3t times 1, 0 plus C2 e to the 3t times 0, 1. We end up with two linearly independent solutions because we ended up with two linearly independent directions in the eigenspace. Anytime the geometric multiplicity is equal to the algebraic multiplicity, you generate enough independent directions in the eigenspace to produce a complete set of solutions. So the issue is not really that we get a repeated eigenvalue having algebraic multiplicity of strictly greater than 1. The only issue arises when the geometric multiplicity is less than the algebraic multiplicity. So let me give you an example of that. As an example, suppose we look at x dot equals 3, 1, 0, 3. As we already know, lambda is 3 with algebraic multiplicity equal to 2. But there only ends up being one eigenvector direction, scalar multiples of 1, 0. So you end up with one solution, e3t times 1, 0. The question is, how do you construct a second linearly independent solution? It's so clear exactly what to do, but you might have an idea based on your experience with the nth order linear case. You might be suspected to ask, can x2 be expressed as t e to the 3t times 1? Does multiplying by t generate something linearly independent? Well, the answer is no, but almost. To see that this doesn't work, you need to see for yourself that when you plug this into the differential equation, you don't get a true statement. We have x2 equals, maybe, t to the 3t times 1, 0. Does this give you a solution? Well, let's calculate its derivative. Well, the derivative is going to be calculated using the product rule. The derivative of t is just 1, so we have e to the 3t, plus t times the derivative of e to the 3t, that's 3t e to the 3t, times the constant vector 1, 0. If we take a times x2, we have a times e to the 3t times 1, 0. The scalars can be moved out into the front. And a times this, we know, is 3 times that because this is an eigenvector corresponding eigenvalue of 3. You can now see that this matches only one of the terms, leaving us account for this. We don't get equality, and hence we do not have a solution. So what do we do? It was a nice idea to try to multiply by t to generate a second linearly independent solution. Let's suppose we have e to the lambda tv, where lambda is, suppose that x is equal to e to the lambda tv, where lambda is an eigenvalue with corresponding eigenvector v. Suppose I try x2 equal to e to the lambda t times tu plus w, where our goal is to figure out what u and w are. We have to assume that this is a solution to the differential equation. So we need to calculate its derivative. The derivative will require that we use the product rule. So taking the derivative of e to the lambda t, we get e to the lambda t times lambda times tu plus w. And when we take the derivative of the second factor, we'll just have u. If we multiply this x2 by a, e to the lambda t will commute out to the front. We'll have t times au plus aw. Now we require that these two be equal in order to be a solution to the differential equation. Every term on both sides has a factor of e lambda t, so we can cancel all of those off. What we need to do next is we need to equate coefficients of t and constant terms separately to each other. Since the equation has to be true for all t, we can set t equal to 0 and just equate the constant terms. This gives us aw equals lambda w plus u, which is equivalent to a minus lambda iw equals u. More on that in a minute. After setting t equal to 0, it becomes clear that the coefficients of the t terms must also be equal. And so we get au equals lambda u. The second equation implies that u is the eigenvector v. Plugging this in up here, we have a minus lambda iw equals v. So to construct our new solution x2, yes, we'll have e to the lambda t tv, which is what we assumed it was before, where v is the eigenvector corresponding to the eigenvalue lambda. But in addition to that, we add this vector w. W is the preimage of v under the linear transformation a minus lambda I. We're going to give these vectors W a name. They're going to be called Generalized Eigenvectors. If lambda and V are an eigenvalue eigenvector pair, and A minus lambda I W equals V, we call W a generalized eigenvector. Our strategy then is to find one solution, e to the lambda t v, where v is an eigenvector corresponding to the eigenvalue lambda. The second solution will be e to the lambda t times tv plus w, where v is again the eigenvector corresponding to lambda, but w is a generalized eigenvector. Going back to our example, x dot equals 3103x, we already have a solution e to the 3t times 1, 0. How do we find the second solution, x2? Well, we need to find a generalized eigenvector. And to do that, we need to solve a minus lambda I v, where we subtract the eigenvalue lambda from the diagonal elements. That gives us 0, 1, 0, 3, 0, 0, and the eigenvector 1, 0 on the right-hand side. You can see that this gives us the equation y equals 1 with x completely unconstrained. So our eigenvectors generally are going to look like this, x1, where x can be any number that you choose. Let's choose x equal to 0, so that our generalized eigenvector is the vector 0, 1. It follows then that the general solution is c1 e to the 3t times 1, 0 plus c2 e to the 3t times t times 1, 0 plus 0, 1. Using a different value of x only contributes something to the other linearly dependent solution and doesn't change the entire solution set at all. Let's look at another example. X dot equals 4, 1, negative 1, 2. We first find the eigenvalues. So we subtract lambda from the diagonal elements, and that gives us 4 minus lambda, 2 minus lambda, and then minus a negative 1, ends up being plus 1. We'll have positive lambda squared. Negative 4 lambda minus 2 lambda is negative 6 lambda, and then 8 plus 1 is 9, which immediately gives lambda minus 3 quantity squared. We get lambda equals 3 with algebraic multiplicity equal to 2 because of the exponent 2 right here. We next need to find the eigenvectors. To do that, we subtract 3 from the diagonal elements and set it at 0. Again, we don't need to write the second row. We only get one independent eigendirection, switching these and changing the sign on 1. This only yields us one solution, e to the 3t times 1, negative 1. To find the second linearly independent solution, we need to calculate the generalized eigenvector. To find the generalized eigenvector, we need to solve the system a minus lambda I v. Well, a minus lambda I is 1, 1, 1, negative 1, negative 1, negative 1. Notice that the second row can be eliminated by a simple elementary row operation of adding the first row to the second row. It's always the case that there will be infinitely many generalized eigenvectors. In this case, we have x plus y equals 1 as the one constraint on the coordinates of the generalized eigenvector W. All you need is to choose 1. Let's set x equal to 1, y equals 0, giving us the generalized eigenvector 1, 0. It follows then that the general solution is C1 e to the 3t times 1, negative 1 plus C2 e to the 3t times t times 1, negative 1 plus 1, 0. Again, we could have chosen any other solution to this equation to add into this spot here, and it would have given us a solution as well. We're now in a position to complete the proof of Abel's lemma. We'll do this in the case of a 2 by 2. In the case where we get e to the lambda tv for one solution, and the second solution is e to the lambda t times tv plus w, where w is in a direction independent from the vector v. You can see then that the Wronskian will be the determinant of e to the lambda tv in the first column, and the second column e to the lambda t times tv plus w. Since e to the lambda t is a factor on this first column, we can factor it out. And we can also factor it out from the second column. We end up with e to the 2 lambda t times the determinant of v and then tv plus w. The determinant is linear in each row and column, which means we can rewrite this as the determinant of v tv plus the determinant of v w. Now, in this determinant, the second column is a scalar multiple of the first column. Anytime that's the case, the determinant will be 0, because it's possible to use an elementary column operation to reduce an entire column to a column of zeros. Whereas, since v and w are linearly independent, this will not be 0. Also, 2 lambda, in this case we had a repeated eigenvalue, lambda and lambda. The trace of the matrix is equal to the sum of the eigenvalues, and so the trace of the matrix will be 2 lambda. Since this is a constant not equal to 0, the proof is complete. This can be generalized with creating additional generalized eigenvectors as preimages of other generalized eigenvectors as necessary. If the geometric multiplicity is 1, but the algebraic multiplicity is 3, you'll need to generate 2 generalized eigenvectors. And to do that, you'll take the preimage of the original eigenvector to get the first generalized eigenvector, and then you'll take the preimage of the generalized eigenvector to get the second generalized eigenvector.